Constraints and basic properties of inverses. Hello, everyone. To begin today's session, let's first look back at what we covered in the previous subsection, where we introduced the concept of an invertible matrix. As a reminder, we established that a square matrix A is considered invertible if there exists another square matrix B such that when we multiply A by B or B by A, the result is always the identity matrix, denoted as I. Now, it is important to realize that this is not a universal rule for all matrices. In fact, not every matrix possesses an inverse. This brings us to our current focus. There are specific constraints and inherent properties that govern whether an inverse exists and how it behaves. Over the next few slides, we will explore these requirements in detail, starting with the fundamental necessity of the matrix's dimensions. Requirement of square matrices. Now that we have recalled the basic definition of an invertible matrix from the previous slide, let us examine the constraints that determine whether an inverse can actually exist. The first and most fundamental constraint you must understand is that only square matrices can possess an inverse. To clarify, a square matrix is simply a matrix where the number of rows is exactly equal to the number of columns. For example, a 2 by 2, a 3 by 3, or more generally, an M by M matrix. You might be wondering, why is this the case? Why can't a rectangular matrix have an inverse? To understand this, let us look at the requirements for matrix multiplication and the identity matrix. First, let's revisit the definition requirement. For a matrix A to be invertible, there must exist a matrix B such that both A times B equals the identity matrix, and B times A also equals the identity matrix. Now, let us perform a dimension analysis to see where the problem arises. Suppose matrix A is a rectangular matrix of order m by n, where m is not equal to n for the product of A times B to be defined, and for that result to be an identity matrix of size m by m, matrix B would necessarily have to be of order n by m, however. If we then consider the reverse product, B times A, we see that since B is n by m and A is m by n, the resulting product will be a square matrix of order n by n. This leads us to the conflict. For matrix A to be invertible, we require that A times B equals B times A, but as we just discovered, A times B results in an m by m matrix, while B times A results in an n by n matrix. Since m is not equal to n, these two products cannot be the same matrix, and consequently, they cannot both be the same identity matrix. To help you visualize this, think of a matrix inverse as a perfect undo button. In a square matrix, the transformation moves data in a way that can be exactly reversed. In a rectangular matrix, however, you are either compressing or expanding the dimensions of the data. It is like collapsing a three-dimensional object into a two-dimensional shadow. Once you have collapsed the object into a shadow, you cannot perfectly reconstruct the original three-dimensional object from that shadow alone. This is why the square matrix requirement is non-negotiable. In the next slide, we will explore what happens when we do have these inverses and the concept of mutual invertibility. Mutual invertibility. Now that we have established that only square matrices can possess an inverse, let us move on to a very important property known as mutual invertibility. The core concept here is quite straightforward. If we establish that matrix B is the inverse of matrix A, it automatically implies that matrix A is also the inverse of matrix B. Essentially, the relationship is reciprocal. To ensure this is clear, let us walk through the logical breakdown step by step. First, let us start with our given premise. We assume that matrix B is the inverse of matrix A. By the definition of an inverse that we have already covered, this means that the product of these two matrices in any order must result in the identity matrix. I, in other words, A times B equals I, and B times A equals I. Now, here is the key observation. If we look at these same two equations from the perspective of matrix B, we realize that the conditions required for it to be the inverse of B are exactly the same conditions we just listed. Since B times A equals I and A times B equals I, matrix A satisfies all the requirements to be the inverse of matrix B. Therefore, we can reach the final conclusion. If B equals A inverse, then it must also be true that A equals B inverse. To see this property in action with actual numbers, let us proceed to the next slide, where we will work through an illustrative example. Illustrative example, mutual invertibility. Now that we have discussed the theoretical concept of mutual invertibility, let us verify this property with a practical example using two 2x2 matrices. First, let us look at the matrices we are given. Matrix A consists of 1 and 2 in the first row and 0 and 1 in the second row. Matrix B consists of 1 and -2 in the first row and 0 and 1 in the second row. In step 1, we will calculate the product of A and B by multiplying the rows of A by the columns of B. We find that the top left element is 1 times 1 plus 2 times 0, which equals 1. The top right element is 1 times -2 plus 2 times 1, which equals 0. For the bottom row, 0 times 1 plus 1 times 0 equals 0, and 0 times -2 plus 1 times 1 equals 1. As you can see, the resulting matrix is the identity matrix, I. In step 2, to test for mutual invertibility, we must perform the multiplication in the reverse order. B times A again, calculating the elements. 1 times 1 plus -2 times 0 equals 1, 1 times 2 plus -2 times 1 equals 0, 0 times 1 plus 1 times 0 equals 0, and 0 times 2 plus 1 times 1 equals 1. Once again, the result is the identity matrix, I. Finally, we reach our conclusion in step 3. Since the product of A times B and the product of B times A both equal the identity matrix, we can formally state that B is the inverse of A, which we denote as B equals A inverse. Simultaneously, because the same condition is satisfied, A is also the inverse of B, denoted as A equals B inverse. This example perfectly illustrates the symmetry we discussed in the previous slide. However, as we move forward, remember that while this worked for these specific matrices, being a square matrix does not automatically guarantee that an inverse exists, which is a critical point we will cover in the next slide. Common mistakes to avoid. First, let's address the assumption that all square matrices have inverses. A very common mistake is believing that simply being a square matrix is sufficient for it to be invertible. This is incorrect. While we established earlier that a matrix must be square to even be considered for an inverse, making it a necessary condition, it is not a guarantee. For example, if a matrix has a determinant of 0, it is known as a singular matrix, and such matrices do not have inverses. Secondly, avoid attempting to find the inverse of a non-square matrix. Some students try to apply inverse formulas to matrices of order 2x3 or 3x2. As we discussed in our analysis of dimensions on the second slide, the requirements for the identity matrix cannot be met unless the matrix is square. Therefore, always check the dimensions first. If the matrix is not square, the inverse simply does not exist. Finally, be careful not to confuse the matrix inverse with a reciprocal. In basic scalar algebra, the inverse of x is 1 over x. However, in the world of matrices, A inverse is not the same as 1 over A. Matrix inversion is not a matter of simple division. Rather, it is a more complex process that involves calculating the determinant and the adjugate of the matrix. Now that we have seen a practical example of mutual invertibility, let us move on to some common pitfalls. It is important to be aware of these misconceptions to avoid errors in your calculations. Keep these points in mind as we move toward our final summary of the topic. Key takeaways. All right, let's wrap up everything we have discussed in this section by reviewing these key takeaways. First, let's revisit the most fundamental constraint we analyzed earlier. Only square matrices, those of order m by m, can be invertible. As we saw during our dimension analysis, rectangular matrices cannot have an inverse because the resulting products would have different dimensions, making it impossible for them to be equal. Second, remember the concept of symmetry. Invertibility is a mutual relationship. This means that if we have established that matrix B is the inverse of matrix A, then it automatically follows that matrix A is also the inverse of matrix B. In terms of mathematical notation, this is expressed simply. If B equals A inverse, then A equals B inverse. It is a two-way relationship. Finally, always keep in mind the core requirement that defines this entire process. For two matrices to be inverses of each other, their product, regardless of the order in which you multiply them, must result in the identity matrix I.